Welcome to Dynamic Equilibrium. Today we're expanding the idea of equilibrium to include dynamic equilibrium. Many chemical reactions can easily run in both forward and reverse directions and are called reversible reactions. This means that even when the overall concentrations are steady, the individual molecules are constantly undergoing change. Think of walking up an escalator the wrong way. You will be constantly in motion, but not progressing.
A chemical reaction at constant temperature in a closed system is in a state of dynamic equilibrium when the rate of the forward reaction equals the rate of the reverse reaction. Dynamic means the reaction occurs in both directions. Equilibrium means there are constant concentrations of both reactants and products in the system. Consider a wet towel hung out on a line. High-energy water molecules can evaporate and are removed in the breeze. This continues until the towel is dry and can be represented by a simple chemical equation. This is an open system. If the wet towel is left in a closed sports bag, it does not dry. High-energy water molecules evaporate and remain as vapor trapped in the atmosphere around the towel. At the same time, low-energy vapor molecules condense on the surface of the towel to a liquid. The rate of evaporation exceeds the rate of condensation until the vapor becomes saturated. At this point, a balance is reached where the rate of evaporation equals the rate of condensation. A state of dynamic equilibrium is reached, represented by a double-headed arrow. Dynamic equilibrium only occurs in closed systems.
As you can see, dynamic equilibrium occurs when the rate of the forward reaction and the reverse reaction are equal. We express this with a double arrow like this. As you can see here, the reaction of A with B to form C and D is occurring at the same time that C and D combine to form A and B. When the rates of the reaction achieve a balance, dynamic equilibrium occurs. This does not mean that you will always have equal concentrations of A, B, C, and D, however. Equilibrium can favor the right or the left, and that is independent of the rates of the reactions.
When heated in a closed system, calcium carbonate will decompose to form calcium oxide and carbon dioxide. As the amounts of calcium oxide and carbon dioxide increase, a reverse reaction occurs and calcium carbonate is resynthesized. When the decomposition rate of calcium carbonate equals the synthesizing rate of calcium oxide and carbon dioxide, the system is said to be at dynamic equilibrium. Now suppose most of the carbon dioxide is removed from the system, and the system is resealed. The rate of synthesis of calcium carbonate from calcium oxide and carbon dioxide will slow down and almost stop. However, the decomposition of calcium carbonate to form more calcium oxide and carbon dioxide will continue. As the level of carbon dioxide increases, the reverse synthesis of calcium carbonate will again begin. Eventually, the decomposition reaction rate will equal the synthesis reaction rate, and equilibrium will be reestablished. But because some of the reactants were removed, the equilibrium has shifted.
As you saw, different things will affect where the equilibrium lies. Those are defined by Le Chatelier's principle, and we'll talk about those in a different lesson. But if the forward reaction and the reverse reaction achieve the same rate, then we have equilibrium. Let's look at some examples. This first example is not actually a chemical reaction, but it does provide a good example of when something is in equilibrium. In the beaker, we have powdered sodium iodine that is radioactive. We pour in a solution of saturated sodium iodine that is not radioactive. If we let it sit for a while, the amount of solid will not change. After a few minutes, however, we can separate the solid from the solution and measure that the solution is now radioactive. Take a minute to talk to your neighbor and discuss why this happens. Solution at the same rate that the non-radioactive sodium iodine is precipitating out of the solution. Let's do another. Some hydrogen and iodine are allowed to react and hydrogen iodide is produced. This is the forward reaction. As the two reactants are used up, the reaction will go slower and slower and slower. However, keep in mind that the hydrogen iodide concentration will go up and up and up. The first key point is that as the hydrogen iodide is produced, it will begin to react and will start to remake some hydrogen and iodine that was used up in the forward reaction. This is the reverse reaction. This has been an introduction to dynamic equilibrium. Thank you.